Across the globe, each legend has its own skyscraper, a symbol of ambition and technology. Though we see them from afar, their true strength lies underground, in invisible foundations. The Burj Khalifa stands on massive web with piles, stable through friction and electrostatic force. The Lotte Tower used deep piles and a thick mat, right beside a river. The Shinjuku Mitsui building rests on wide left, placed directly on the ground. Different method, same goal. To support the building, these unseen foundations are what makes super tall towers possible. Each system adapts to soil, weight, external forces, and available technology. So, what supports this building? Yokohama's land was reclaimed from the sea, starting in the late Edo period. Most of Minato Mirai 21 took shape between 1983 and 1989. Reclaimed land has layers: surface fill, sand, and clay, industrial debris, then natural ground. Yokohama is no exception. Many buildings here use the piled left method. Left foundations alone can be risky in soft soil, as they may settle unevenly, so piles are driven down to each farm ground. Given those conditions, we assume this building used that method too. After some delay, we found an article mentioning a direct foundation. Using a direct foundation on soft reclaimed land, it seems unlikely. Wouldn't the building sink or collapse? Yet, this tower stands on a huge mat poured right on the ground. Usually, solid bearing layers are over 40 meters deep, with uneven slopes and unstable ground. That's why direct foundations are rarely used. But this site was different. A stable, flat-bearing layer was found just 5 meters below the surface. Other sites in Yokohama had uneven dips even within the same Kazuma Formation, but this plot has surprisingly uniform and stable ground. It was, in every way, ideal for building a super tall structure. Beneath the site lies the Kazuma Formation, a geological layer from 5 to 90 meters deep. Its axial compressive strength is stable, averaging 33.5 kgf per centimeter square. Made of compacted silt and clay, this layer has high shear strength. Shear strength is defined by internal friction angle and cohesion, as explained by Coulomb law. Thanks to its strength, even at 90 meters deep, this formation ensures high ground stability. Typically, clay has a high Poisson ratio, which causes sideways deformation under weight. But the Kajasa formation is densely cemented, with a low ratio, so it's barely deformed. That's why this layer, just 5 meters below the surface, was ideal for supporting the building. They dug about 20 meters down for the basement and placed the mat directly on it. It covers our entire base with reinforced concrete, or even support a quick resistance. This mat supports about 330,000 tons of building load from the third basement and below. To avoid stress, Built up under the column, the mat was made 5 meters deep. Now, excavation begins. Let's move to the construction site. To build a foundation on palms of soil, deep digging was required. Ground collapse was a real risk, so they used a bottom-up method, removing 660,000 cubic meters of soil. Excavation reached ground level minus 24.1 meters in the higher rise zone and minus 60.35 meters in the low rise area. As they dug deeper, more challenges came up. Groundwater seepage, weak soil collapse, and ground rebound had to be addressed. To hold the soil, they built a continuous wall using soil cement columns. Since the site used to be a shipyard, many barrels of ticker has to be removed. They used a rock auger drill to cut through debris and make space for the wall. The main challenge was structural strength, so they reinforced the piles by embedding H-shaped steel beams, totaling about 2,500 tons. Each pile was 650 millimeters in diameter. It also improved stability when earth anchor was installed later. After building the retaining wall, they installed removable earth anchor. Each anchor handles 65 TF of pulling force, with up to 7 layers used based on depth. These were vital to reinforce the wall, which alone weren't enough. Now, it was time to build the actual foundation. Hyundai LCT, Lotte Tower, and Worship Grand in LA needed a massive volume of concrete for the mat foundation. At LCT, 8,600 trucks poured 40 MPa ultra-strong self-compacting concrete. Pouring lasted 39 hours, 18 for Towers A, 21 for Tower B. The hardest part was controlling the heat from cement hydration. To solve this, they used ultra-low heat concrete, 70% post-cement, and 30% fly ash. Real-time temperature monitoring and field response system were in place. But surprisingly, this tech had already been used 20 years earlier in Yokohama. At Yokohama Tower, a 5-meter thick mat was poured continuously for 40 hours. The mat foundation will reinforce concrete. The main challenge was placing the lever and controlling heat from hydration. To reduce heat, they use FMBB cement, Type B slag mixed with 20% fly ash, unlike typical MBB. This project needed 60,000 meters of continuous concrete. The precise summer control was essential. FMBB generated 13% less heat than MBB, and only 45% of that from ordinary cement. Slump and strength control were also critical. They aimed for the 20 plus minus 2.5 cm slump and 240 kgf per centimeter design strength. The actual mixed strength was 302 kgf per centimeter with a 5% water cement ratio. But one question remained: how did they pour so much concrete at once, given the old pumping tech? In most large buildings, mat foundations are poured in segments, but not here. That method was rejected for two reasons. First, it could cause too much tension in the lever between segments. Second, joint between segments should let underwater in corroding a steel. So instead they use a Smeric branching pipe system for continuously pouring. Scratch pipes were laid out in advance, with hundreds of outlets for even distribution. The site was divided into 10 zones, fed by horizontal pipes. These pipes supported 320 vertical lines spaced 28 meters apart. At concrete filled the vertical pipe, workers manually cut them to match the rising height. The concrete from each pipe covered an area of about 17 square meters. Each pump truck needed 16 crew members, one hose and one vibrator operator per line. With this setup, the entire mat was poured non-stop over 39 hours and 30 minutes. An average slump of 13.4 centimeters, air content of 3.9%, and a placement temperature of 27. Final compressed strength averages 315 kg FCM, exceeding expectations. In the heart of city, non-stop concrete pouring for 40 hours was monumental task. We had to supply 600 cubic meters of concrete every hour. 10 ready mix plants within 40 minutes were selected. 5 of them could operate through the night. In just 2 days, over 5,000 truckloads were mobilized. On July 7, at 7 a.m., the pour began. Each horse delivered just 7.5 meters per hour per precise compaction. The pour moved slowly, only 11 centimeters per hour. The Yokohama Landmark Tower stands on reclaimed land. Normally, a soft ground like this demands pile. But this site was different. A shallow, flat Kajisa layer made direction foundation possible. Upon it, we poured a 5-meter thick mat for 40 hours. The concrete never stopped. With 600 MPa lever and double reinforcement. Over years of monitoring, settlement remaining just a few millimeters. This building is proof. When soil, structure, and construction are precisely calculated and brought together, greatness isn't just possible. Next week, we will explain lever arrangement of mat foundation and four main columns.